Almost every VQA model predicts short labels, but a generative one, it need to speak, and to do that we need strong architecture that understand images, understand text, and then generate answers step by step. So in this video we are going to build exactly that. Hello everyone and welcome back to Generative VQA series. And up till now we have explored first the fundamentals of VQA, their type and the challenges involved. Second, the full architecture that we are going to build. Third, we have deep dive into the VQA version 2 dataset that we are going to use. In the last video, we have prepared a mini dataset from the VQA version 2, and that dataset contained descriptive answer. From that, we have removed all the small one word and two word answer. So now we have a small dataset of about 9k question answers. So we are going to use that. Now in this video we'll work on implementation of the generative VQA model using CLIP for image encoding, GPT-2 for question encoding, and a GRU decoder for generating the answer token by token. So first of all, we are going to import all the libraries that we need for this task. So here PyTorch is our main deep learning framework which we are going to use. Next we are using CLIP for image encoder, and then we are using GPT-2 from the transformer for question encoding. And remember, GPT-2 is for question encoding, not for generating answer. Some might may be confused because GPT-2 is a generative model, but remember it's a too large model to train or even fine tune on a 1050 Ti. And remember, all this is going to be done on 1050 Ti. So we have used GPT-2 for question understanding, question encoder. So let's start with our main class, and let me copy some part of the code and we'll explain it. So here we have our VQA model class. So this is our vocab size. So this is just a size. It would be around 2.5 to 3k, because we are using a custom GRU and a custom vocab for our answers. So in this model there will be two kind of vocab. First would be the question one, which is GPT-2 model would handle itself. Then we have answer vocab, because initially I started using the GPT-2 vocab which is around 50k to generate answer for these answers, but that was too big to optimize and to train. Then I thought about let's use our own, and then things became much easier. So what I've learned over this is that if you are working on something simple, you don't need to jump directly to transformers, especially in term of training. You can use them to extract features like what I'm going to use. I'm going to use CLIP for feature extraction. I'm going to freeze them, and same for GPT-2, that for question understanding I'm going to freeze that also. So I'm not training them. But in term of training, make sure your things are, if your data set is simple, just use simple thing like GRU. Why transformer? GRU is simple. Transformer is needed when you are generating longer sequence of text, because it contains self attention. That's why our vocab size is small, because we are using custom vocab size and a GRU. So here we have few variables, arguments: max question size, max question length 16, max answer length 10, hidden state 256, then number of layer, and this is for the GRU. Then a dropout. What is the device? So by default we have said CPU, and where we have few tokens like pad token value would be 0. BOS basically refer to beginning of sentence or sequence. So its code token ID would be 1. Then we have end of sentence token. Its token ID would be 2. Then we have unknown token ID. Maybe sometime we have some token for which we don't, which is not in our vocab. So for that we have 3 token ID. So these are essential thing, because padding is used to pad the empty spaces, because we need batches, and we need to make sure every batch, every entry in the batch would have same size. So we pad them like we pad the question. Okay, so let's say we have a question of some length, not all question would have same length, so we fill the rest with pad token id. Then we have bus, it indicate the sentence has started. eus, it indicate that sentence has done. So here we have initialized them. Okay, so this need not to be done now, so we are not doing fine tuning now. So let's remove that part of the code to make things simple. And then we have given token IDs here to each variable, because we need to use them in every function. Next, we are going to load our CLIP model. So here is our CLIP model. We load VIT B2 on our CPU for now, and we're going to change it to GPU, just remember that. And here specifically we have said every parameter required grad equals to false. So what this does is it makes sure that all the parameters are frozen. Okay, this is what we do, we froze them. So we are not training CLIP here, we are just using it for feature extraction. Just that we give image to the CLIP, CLIP give us some feature at the end, that's it. We are not dealing what is inside CLIP, because we already know it is trained, it is much better than anything. So because we are not doing any training, then let's use the best thing. That's why I've used CLIP here. Instead, even because my GPU is 1050, I can use even like MobileNet V2 or V3, something small. But if you are not training, why take any tension? Just use one of the best thing. That's why I've used CLIP. Then for the question encoder, we are using GPT-2. So here again we are using GPT-2 from transformer, that is a pre-trained, and we are using distill GPT. It is much better, it's not that heavy. We load it to our device, and again same, we are frozen it, we are not training it. Okay, that's what we are doing. So now let's move on to encode image and encode question, because those are two important functions which we have. Okay, let me reduce the zoom a little bit so that I can see the entire thing at once. Okay, so here we have our encode image. So this method, what it does, it basically receive an image and it give it to the CLIP model. It encodes and do all sort of thing, and then we get our feature. Simple. So now let's deep dive. Okay, so we have this fine tune thing, we need to remove it. We are not fine tuning it, let's make it simple. Or even we can let it now. We can say again, like let's leave it for here. We can again define as for now false. That is nice, because see, my plan after that is that I'm going to do some transfer learning, basic transfer learning on this, and then later if you need, I have also a video planned for fine tuning, just few layers of this, a clip and few layer of GPT-2, and those can be done on 1050 Ti. So that's why initially I have just these things. Okay, so what this image encode does is the method passes image to the CLIP encoder. By default, CLIP is frozen to prevent training, and it gives you an output vector which is L2 normalized. Here you can see we normalized it. And then we get our feature as a floating point 32. This is simple. Next we have is our question encoder. Let me copy that part also, and it's a bit complicated, not that complicated, but bit more complicated than encode image. So this GPT-2 which we're going to use to encode our question is going to take the input ID, then attention mask. So we all know, or not all questions are same. This would be list of integer and this would also be a list of integer. It would contain 1 and 0 value. So here it would have the token IDs, basically the integer value associated, and to fill it we also have padding value. So in the attention, what it does is, if for the words, for the tokens, it has a value 1, and for the padding it has a value 0, so that the model knows which are real value and which are padded values, because padded values are not important, they are just to fill that gap. So that's why we have attention mask, to show, to indicate. Oh sorry, my bad. So it would return you the last hidden state. Okay, because we want single embedding per question, not a token. Okay, and here what we do a mask mean, basically, because what we don't need individual token, we need a sentence embedding. For a question we didn't need a single embedding. We are not doing complicated thing like using embedding for each token is much better, but at the initial stage it's better to use a sentence embedding. So what it does, first of all, we extract the token level embedding in this line. Okay, it would give you the last hidden representation. Then we apply the attention mask. Here if you see, we apply the attention mask here. So this removes the padded tokens from the representation, because padded tokens are not important, so they would unnecessarily harms our quotient representation, quotient features. Then in the next few lines we compute mean pooling over the non padded tokens. Okay, so we do a mean, we get a mean feature representation of all the tokens, excluding those padded tokens, and at last we do a normal L2 non, and we get our text feature, that is our question feature. So this is about our encode image and the encode question. Now let's do one thing, let's run them and test them. So first of all, what we need is our model. For now let's run it on CPU only and see. So first of all, what we need is an image, a fake image. So this is our fake image. So it would give image features. So we would say model dot encode image. Am I doing it right? It's not giving autocomplete. That's fine. Fake image. Now we're going to print its shape. Shape is important in deep learning. Shape is everything. If your shape is messing up, then you may not work. Let me activate my PyTorch environment, and let's run this thing, see how it works and what error it gives you, or it runs successfully, anything. Okay, so we have our 512 embedding, simple. So this one is working fine. Now we need to see another thing. So what we need now is fake question and fake question mark. Let me comment that out. So these are fake question ID, fake question mask. See, now we'll understand the question ID and the mask. So this represents something, this represents something, this represents, but this represents 0. This is padded token. So that's why we have 1 here. They represent something, and we have 0 because they are padded to represent. Now what we do is we give that to our encode question and we print its shape. See how it work. Again, see any error, problem, or how it work. And now you can see we get a sentence level embedding, and the output we get is of size 768, and for the image it's 512. So now till now things are working fine. Now what we need is we have both the thing. Okay, so let's now write the forward function from where the execution begin, and we'll see how we're gonna work. So what do we need here? Spelling mistake. We need images, fine. We need questions, good. We need answer, input, IDs. So this is a special thing. By default it's none. It's going to be used during training because we have a method called teacher forcing, and we also, so during teacher forcing we're going to give answer to it, the real answer, but during inference we only give question here, so that's why it's an optional thing. So what do? We first encode the image, just like what we done here. We're gonna comment it out. Let's uncomment these things because we need those inputs. We don't need them to execute here. Okay, so these are our image. We give image to encode image, we get its feature, image projection. We're gonna write the thing, don't worry. We have image feature. Next we have questions. Okay, so now we use encode question, we give it the question, input IDs, attention mask. If we get the question feature, we pass them via the question projection and we get the question feature. So what is this projection? Basically these 512 and 768 representation which we get from encode image and questions respectively, we convert them to common representation. So what it is, basically it's basically some layers, some linear layers which we need to put. Okay, let me simply paste them. Just a second. Okay, yeah, so these are the projection layer. We convert them to a common like dimension, a common space, so that it's easy for us to combine them, fuse them, because if one is 512 and another is 768, it's really difficult. And because for our answer both the features are important, so we need to combine them in some way, and combination would be easier if they are of same size. That's why we convert them to a common representation. Okay, next what we need to do is we need to fuse them. That is the next important thing which we need to do. So let's learn the fusing here. Let's define that. So we have encode image, encode question. Now we come to the fusion part. So fusion is simple. It's not that complex. It's really one of the simple fusion that we can do. So what do we have? We have the image feature and the question feature, and these are when we pass them via the projection, a common, which they have common representation. So we simply concatenate them and we pass them via the sigmoid, and inside that we have a gate layer. So basically a linear layer which passes via the sigmoid. So we have this gate. So it's basically a value, a vector, okay, a single value. So this gating mechanism decide how much weight is going to assign to the vision, that is the image, and how much attention it's going to assign to the question. So it plays, let's say if gate is near equals to 1, it focus more on the image because see, first is image. If gate is near to 0, it would focus more on the question. And let's say it's 0.5, it's gonna focus equally on both. So this is how it works. It over time learns and try to compensate information from both image and question. And this could also be case that it may only use one at a time. This is automatic, but here it's learning. So I assume because we are using descriptive information, and for those it need both the thing, and this is one of the simple thing which you can have, a simple kind of fusion. You can even have more complex fusion, you can use them, and also comment that out, how they work for you, how you can improve this. Like, improvement is always there. What I'm showing you is a simple thing. Now let's define all the layers, all the linear layer which are there. What we can do, we can first, like, I can define all the linear layer for you. Otherwise it would be difficult to like jump here and there. Okay, projection layers are done. I have unnecessarily copy them. So this is the fusion module. So we have gate layer where we have concatenated both the image projection feature and the question projection feature and convert them to hidden representation. It passes via the sigmoid and we get a gate function. Then we do a gating mechanism, combine both the image and those feature. Then we pass that fused feature with this fusion. Okay, hidden state 3. Let me show you why. Hidden state 3. Here is the fusion. So for what we have is the fused and the X, both, also the concatenated. That's why hidden state into 3, and we get a representation at the end. And then it's all related to the GRU and the output. So it is the embedding. It take the input of the vocab size and convert it to a hidden size. Embeddings are basically a better representation than those integers, these integers. Okay, then we have a GRU. Hidden size is input size is hidden size by 2, hidden size number of layer we defined as 1. Then we have dropout here. Then we have layer normalization for GRU specifically. Then we have the output layer equal, which take hidden size as the input. So hidden size would be the common unit here. Every layer would take some form of input and output would be equals to hidden size. So this makes things easier for us to combine and work with because we know what is the common unit. You can of course change them according to your need. Now what we have done till now, we have come with a fusion. So let's fuse them in our forward function where the execution by default happens. So here we have the fused feature, image question, image feature, question feature, and we get a context. So this is our context now. So we also get our batch size. What is our batch size? Now comes the important thing, that is our GRU, where we need to generate, which would generate answers token by token. So first of all, we are going to initialize the hidden state for our GRU. Every recurrent neural network take 2 input. First is the main input, second is the hidden state. So for first iteration, its hidden state would be 0. Okay. So this is number of layer, then batch size, then hidden size, then the device and the data type. Now remember, here we have 2 things. First is teacher forcing, then auto-regressive inference. So what I'll do, I'll completely paste both of them, each line of code. Okay. And I need to make sure this is same as here. Yeah, now it will work fine. Okay, so now what I'll do, I'll explain each of the thing to you. So first of all, let's understand what's the difference between teacher forcing and this auto-regressive inference. So see, both the strategies are used during sequence generation, like what we doing here. So first let's understand teacher enforcing, what it is and how it work, how it help. So see, teacher enforcing means during training, the model is given correct previous token instead of its own predicted token. So we all know things work token by token here. So we're going to give BOS at the starting. What we do in auto or regressive, we give it the BOS token, then it give it to the GRU give its own token, then that predicted token would be added to this, and then those two would be given as the input. But we don't do that thing in the teacher enforcing. So during training, what I'm saying, let's repeat it again. The model is given the correct previous token instead of its own. So this makes training faster, more stable, because GRU also always received those correct token from the data set. So due to this, error don't accumulate across step, and the model learn how to predict next token under ideal condition. So in overall, this makes the training faster and more smoother. This is a much better way. So for initial, this is the best way, and you should always start with teacher forcing. So if you understand it by an example, so we can say it's like teaching a child to speak by giving them correct next word during practice. But this is only used during training. Now let's come to the auto-regressive generation, which we use during inference. And so during inference, the model feed its own predicted token back into the next step. So we start with BOS, that is beginning of sequence or sentence, so that model knows now I need to generate sequence. So it give it to the GRU, it predict the next token, okay, and then we do it until we receive EOS or we hit the max length, and this next token would append back to after the BOS. So we have BOS, let's say it generate I, the next would be BOS I, it would be as the input, then again, so it would work like this. And that is what is in these all lines of code. So see, this is the sequence length. First of all, we need it because we need to expand something here. Then we have the embedding. We convert our answer input IDs. This is the answer. We convert it to embedding. We expand the context. Okay. Because now our size also change. We have a sequence length here. Okay. So this is the batch size and sequence length, the hidden state. So hidden state is always less, last. Then the GRU input would always be the concatenated of the embedding, that is the input and the context. So this is basically the context. So context is what? The fused feature. Then we give it, now the GRU input is the main input in the hidden state, and GRU outputs the GRU output and the hidden state. So all these things are, all these things have a three-dimensional shape. What I mean by that is batch size, then it has sequence and the hidden state. So this is always remains like this. Okay. So here embedding is also in the same way. Context is also in the same way, in the same shape. Like the values may be different, but it is like batch size, sequence and hidden state, something like that. So their values could change, but the representation is like that. Then GRU output is also in the same shape, hidden is also. So then we take the GRU output, we pass it via the ln GRU, we pass it via the layer normalization. Okay. So it helps. Then we passed this again, the output of layer normalization GRU via the self output. Now the size of the input, the GRU, the input to the output layer, that is GRU output, is like this. So it get converted into this vocab size for each of the word in this sequence. It would get a vocab into like vocab size, so that for each we have the token. So this is how it works. I hope like you understood. Like if you write it yourself and do some hit and trial, you would understand it much better. I'll explain it again and again. You can see the video again and again. So it's fine, but until you try it, it won't work. Now let's do this auto regressive thing. So here what we have a generated a variable in the torch, basically a tensor. Its size is batch size by answer length. So this is basically our answer, but we have filled it with padded token ID, and its data type is long, and placed on our CPU or GPU. So we start with BOS, say at the index 0 we place BOS. Then we run a loop over the answer length. So our current input would always be generated this minus t minus 1. So t is the current state. So before current state would be our input. Then we pass our input to the embedding. See, if you are confused, see at the 0, see it start with BOS. This is our 0 state. Let me comment it out. But we start loop from 1 to max answer. So it says 1 minus 1 is 0. So it would give this. So let's say if it has I M. So this is our sequence. So it would always be a step back. This is our current input. We pass it via the embedding. Okay. And we do some unfloat, unsequence. Again the same thing, like for this three-way representation, batch, sequence, and hidden. This is how it works. Just remember that, like when you work with deep learning, shapes are really important in itself. Then we concatenate that, we do calculations same way, just that here it is in loop for individual tokens. We give embedding and the context expanded. This act as a GRU input. Along GRU would take the GRU input and the hidden state. It would output GRU output and the hidden state. Okay, then GRU output would pass via the layer normalization. We pass it via the self output. Same way we have done above. And if would give you the logits, the row value. Then we use the row max to get the next token. But basically this is the predicted token, and we add it to our this generated t. Now remember why we do t minus 1 every time when we start, because at the end in the generated we have the token, the generated token. And if we encounter end of sequence token ID, we're gonna stop it and we give back our generated token. This is how it would work. So I hope I have explained you like both the teacher forcing and auto-regressive inference in a way that you at least get some part of it. Maybe you won't be able to get whole part, because just seeing and writing piece of code is not enough. You need to write it yourself, and that would help you with it. If you at least are able to get some part of it, that is also good, because at least you get something. And when you write the code and do it and like get some error, see, errors are essential. If you don't receive any error, this means either you are super genius or you are not doing anything. So this is, I think, the entire model, and for now we don't need anything, but later on we would have some more part added into it for the fine tuning. Simply we just unfreeze some layers, some last layer, like 2 layers from the clip and 2 layer from this GPT-2. So we don't do that, and also fine tune them. So let's at last let me copy paste that part of the code where we do complete testing. Okay, so we have this. Let me remove this part of the code. Not essential. This is not essential. Okay, so we have this. Okay, I am now confused. So we have the model. Okay, got it. So we need to give the output. We have the model. We need to give it the fake image, and I need to give it the question batch. Okay, now let's print the fake output, what it gives you. Even I don't know what the answer is. That would be interesting to see what it learns from random image. And because we don't have any tokens, oh, okay, you can see it gives you some token Let's see how random they are. Okay. Okay, so there's some randomness in this. You can use seeding to stop that randoms, but that's not an issue. The main thing is that we have implemented everything and understood maybe some part of it, not whole. So that's all for this video. So I hope you have learned something from this video, and if you learn something from this video, please subscribe, like, and share it with your friends. And if you haven't watched the previous part, then please do watch the previous parts also. They're also important. Mostly they are theory, but like the last video is really essential. If you can watch that, like where we created a sub data set from the VQA version 2, and here is the folder where we have this, and here's the complete code for that. It's not that big, it's just half an hour video, you can watch that. So in the next video we will be moving on to the dataset pre-processing, where we pre-process image, tokenize question and answer, and then creating PyTorch dataset and data loader. So stay tuned, we are very close to training the entire generative VQA pipeline. So thank you, have a nice day.